to introduce our speaker today, Dr. Rita Kounoudis. Rita's work in seismology began during her PhD at Imperial College London, where she was using tomographic imaging techniques to look at subduction processes and slab break-off in Eastern Anatolia, as well as rifting in East Africa. Now she's a postdoctoral researcher at the University of Oxford, and she's here to talk to us today about some more recent work on crustal and mantle seismic structures seen in the East African Rift. So whenever you're ready, Rita, it's all yours.
Thanks, Sophie. Thanks to the COMET group for having me. And well, today I thought I'd take you on a journey to the East African Rift, which is where I spent most of my PhD working on. So it's an area that's experienced significant flood-basaltic magmatism in response to a mantle plume. And most notably, it's formed this really massive flood basalt province that sat right on top of the Ethiopian Plateau. So the lithosphere, in response to this, has been significantly modified, and we can observe this seismically. So where there's been lots of magmatic intrusions in both the mantle lithosphere and the crust, they'll typically alter the wave speed structure of the lithosphere, and you end up with a profile much like the one on the right here, shown in red. In comparison to what you would normally expect, where you have relatively unmodified lithosphere in response to a plume. So whilst this is the case in sort of the northern part of the flood basalt province, what I'm mostly going to be focusing on is the region immediately to the south of it, which is very different. It's a very low-lying region. It's got this massive lake right in the middle of it. So instantly we're looking at something that's quite different structure-wise. But this area is also underlain by a mantle plume. So part of this talk is going to be exploring the lithospheric modification of this region and how it compares to the north. And ultimately, we're going to talk about why the flood basalt province is focused in the northern section of East Africa, as opposed to further south. Right, so a bit of background on East Africa. Like I said before, it's underlain by mantle plumes, and that's what's thought to have given rise to these uplifted plateaus and very extensive flood basaltic magmatism. However, this region to the south, called the Turkana Depression, has actually experienced a previous phase of rifting that's trends northwest-southeast, that sort of pre-rifted the lithosphere prior to the arrival of the mantle plume. So we want to explore the seismic structure of this area and see whether it's similar to further north, where we have this extensive flood basaltic province. So what things we're going to be focusing on is the Moho architecture. So seismically, you'll be able to see a transition to faster mantle wave speeds, and that's expected to be sharp, where you don't have lots of magmatism. But expected to be blurred where you do have a significant amount, such as further north below the flood basaltic province. And we're also going to explore the mantle lithospheric structure, where you would normally expect unmodified lithosphere to retain this fast wave speed lid. To the north, it hasn't quite done that. Everything looks a lot more slow and heavily modified. And that means that we don't get a very clear picture of what the lithosphere-asthenosphere boundary is in a region like this. So which is the case below the Turkana Depression? Has it been modified to the same extent further north? What is the impact of these previous rifting phases on the modification of the lithosphere? So as well as that, we're going to be looking a little bit about how rifting developed in this region. So we know to the north and the south of it, rifting is quite focused, but within the depression, it seems to span a much broader 300-kilometer wide region. So is the style of rifting here magmatic or more mechanical plate stretching type rifting? So as I mentioned previously, the main Ethiopian rift and the eastern rift to the north and south of the depression, in these narrow rift valleys, appears to have been magma-assisted rifting. So all dike intrusions and sills in the crust accommodate a significant amount of the extension. However, whether this is the case below the depression is uncertain. So for starters, something that might indicate that it's different is the presence of that fault-bounded lake that indicates more mechanical type rifting. And also quite thick sedimentary basins to the west of the lake, which is where most of the East African rifting developed within the depression. So that's pointing to something different mechanically. However, there are similarities, such as these volcanoes that follow Lake Turkana, and a lot of the recent basalts that have developed here have very similar characteristics, such as those in the main Ethiopian rift. So what we're going to do is we're going to use our seismic velocity profiles and structure that we're going to derive to try and understand whether rifting was more magmatic or more mechanical, and therefore different to the surrounding regions. So another question we're going to explore is where did the rifting actually develop throughout the Miocene and in the Turkana Depression? So it doesn't seem to follow this simple straight line fit between the Eastern Rift and the main Ethiopian Rift. It seems to have developed mostly to the west of the Turkana Depression. And a lot of modelling studies thus far have modelled the depression as this simple, uniformly thinned lithosphere because of these previous rift systems. But in the absence of any lithospheric scale constraints, we don't really know whether this holds true. So that's another goal. We want to try and see if we can image the lithospheric structure and how it varies across different tectonic domains in the depression, and hopefully inform some future modelling work. So to do all of this, we first had to deploy a seismograph network because this region has never really had a seismic deployment within it, in contrast to the surrounding parts of East Africa. So as part of the Trails project, we deployed a series of 35 broadband seismograph stations. So they're shown by these triangles in the middle of the depression. And we left them there for about 2 years, and we recorded as many earthquakes as possible in order to seismically image the subsurface. So I should mention there has been one permanent station deployed in the region. So that's the station here noted by a star. But everything else has been recent. And because it's always fun to show, here's a video of us deploying a seismometer in southern Ethiopia. So this is located in a school right on the border between Ethiopia and Kenya. So what we do is we'll typically bury our seismometers. They're broadband seismometers, so they're capable of recording earthquakes on a broad range of frequencies. Sorry about that. Yeah, so they're broadband instruments. So they can record earthquakes on a broad range of frequencies, both local and teleseismic. And we connect them to a solar panel in order to get a source of power, because we typically leave these in quite remote regions. But yeah, field work is always great fun. It's probably the highlight of my PhD project. And then we'll bury them and return to them 6 months at a time to do our data download. Right, so with this data, one of the first things we did was image the mantle using body wave tomography. So we wanted to see if this low-lying region is also underlain by plume material, now that we actually have seismic coverage right within the depression. And what we find is that there is slow wave speed material pretty much everywhere below East Africa. There's no break in the continuity of these slow wave speeds. So the depression is definitely underlain by warm, buoyant material that's likely related to the African superplume. So not very different to where the flood-basaltic province localized further north. And in fact, there actually seems to be a faint plume tail right below the Turkana Depression. So that's quite a new sort of finding from these models. But what we find in the crust is that it's significantly stretched. So crustal thickness reaches up to about 20 kilometers below and to the west of the lake. And stretching factors would have been quite high, so more than about 2, a factor of 2, which is more typical of a mechanical type stretching as opposed to magma-assisted rifting, where you wouldn't expect to thin the crust as much. But despite having a thin crust, which probably gave rise to its low elevation, and being underlain by a mantle plume, its crust is relatively melt poor. So we can see on the right VP/VS ratios for the bulk crust, and most of them are quite low. So all these blue values here, 1.7 roughly. So that's typical of areas that haven't experienced much mafic intrusion. And it's not too dissimilar to what we see in the craton to the south. Whereas in the Ethiopian Plateau to the north, a lot of these receiver functions would end up giving you a high VP/VS ratio, indicative of lots of melt. But that's not the case here. So interestingly, we're in an area that is underlain by a plume, but hasn't experienced as much magmatism. So what we want to do next is try and have a look at the mantle lithospheric structure and see whether that has been modified by melt, and can we actually see a lithosphere-asthenosphere boundary below the depression. So to do that, we use surface wave tomography to get a good idea of lateral wave speed variations in the crust and the uppermost mantle. So we do that by using Rayleigh waves, so it's a type of surface wave, from regional earthquakes, so earthquakes that occurred within about 3,000 kilometers of the depression. And we exploit the dispersive nature of surface waves, where you get a different group velocity as a function of period, which is sort of analogous to depth. So after acquiring this data set for all of these different earthquakes, we ultimately invert them for group velocity variations as a function of latitude and longitude in the depression. And this is an example at 30 seconds period, which is roughly, its best sensitivity is at roughly 30 kilometers depth. So this is great. We've got a good idea of what the lateral variations of wave speed are, but we don't have much information on the vertical resolution and how wave speeds vary with depth. So surface waves aren't very good at providing that information. So to get a better picture of how wave speeds vary with depth, we jointly invert these surface waves with receiver functions, which are very good at pinpointing depths to discontinuities below the subsurface, such as the MOHO or the LAB. So what they'll do is they'll measure both the direct arrival and reverberated phases in order to give us a good idea of what the crustal thickness is below a region. So jointly inverting them together gives us a 1D velocity profile in quite a lot of detail below each seismograph station. And the features that we're most interested in is this crust-mantle transition. So that's at the base of the steepest velocity gradient, would be where the MOHO is. But then we also get a good idea of where the LAB is, and that's where you reduce from faster wave speed, faster wave speeds in the mantle lithosphere to slower wave speed asthenosphere. So that is typically what the proxy is for the LAB. So just a quick recap, the features that we're looking for in terms of whether lithosphere in the Turkana Depression has been heavily modified or not are summarized here. So on the left, for example, you can see a relatively melt-poor lithosphere. That would give you something like profile A here. A nice sharp MOHO because of the lack of low crustal intrusions, and then a nice fast wave speed lid that's from which you can clearly pick out an LAB. But on the right, which is much like what we see in the Ethiopian Plateau, heavily modified, big low crustal intrusion complex, blurs the transition from crust to mantle and also from lithosphere to asthenosphere. So we're going to look out for these features below the Turkana Depression and see how it compares to the north. So first, to talk to you a little bit about what we see in the Ethiopian Plateau is we actually see a very thick lower crustal intrusion layer. So the Eagle project on the northern end of the main Ethiopian rift and flood basalt province, so using wide angle seismics here, for example, they imaged an 8 to 12 kilometer thick lower crustal intrusion layer that pretty much spans everywhere west of the main Ethiopian rift. So that's quite extensive, and that's where most of the flood basaltic magmatism seems to have focused. Looking deeper at the LAB, we don't see a clear signature of it. So where you would normally expect to see these negative polarity S to P conversions where the LAB is located, you typically don't see it anywhere. So that's telling us there isn't a big jump in wave speed between what's lithosphere and what's asthenosphere. We can also see that in 1D velocity profiles from previous studies that show this really thick gradational moho and pretty much no evidence of an LAB anywhere where there has been flood basaltic magmatism. So this is the picture in the Turkana Depression. So to focus you on the moho at shallow depths, what we see is that the wave speeds are actually quite sharp, much sharper than what you would find in the Ethiopian Plateau. That's this line here. And it's pretty much the case everywhere below the Turkana Depression. So that's suggesting we generally lack lots of lower crustal intrusions and active melt. In fact, what we're looking at looks a lot more like the Mozambique belts, which is all the way down here in the south. And that's not experienced as much magmatism as further north. It's a very melt-poor region. So the Turkana Depression seems to be a lot more similar to that in wave speed structure. Peering deeper into the lithosphere, so focusing on the mantle lithospheric structure, we can see this nice fast wave speed lid that is typical of lithosphere that hasn't been magmatically modified to a large extent. So again, below the plateau, wave speeds are a lot slower. But everywhere in the depression, pretty much, you get this lid. So that's suggesting a lack of heating and thermo-mechanical modification. Except for one region, and that's the region to the west of the lake, which is where I mentioned earlier most of the Miocene to recent rifting has focused. So we can actually see that there is a bit more of a gradational moho in comparison to elsewhere. So it's starting to look a bit more like the Ethiopian Plateau, but still not quite as gradational. And mantle lithospheric wave speeds are a lot slower. So nothing like what normal mantle wave speed is, which is what this dashed vertical line is showing. So this makes sense. This is where most of the magmatic rifting has developed. So what we did was take things a step further by converting our wave speeds to mantle temperatures to get a good idea of the thermal structure of the lithosphere and the underlying asthenosphere. So we used periodicitic composition to do the conversion, and we took into account anelasticity. And this gives us another independent proxy of where the LAB would be. So thermally, the LAB is often defined as the intersection, I guess, between what you would class as a conductive geotherm in the lithosphere and an adiabatic convective geotherm in the asthenosphere. So the intersection of that would give you what the thermal LAB is. And that's sort of consistent roughly with where we seismically see the LAB. Although that one's a bit shallower because well, the thermal LAB would generally correspond to a minimum in seismic velocity as opposed to the steepest gradient. The slight variations there. But looking into the asthenosphere, the best fit mantle adiabats gives us a good idea of what the mantle potential temperatures are below the region. And everywhere in the depression, we get elevated temperatures, so 50 to 150 degrees C above ambient mantle, confirming again that we've got the same plume material that's pretty much located further north. So to put things together, I guess, why is the Turkana Depression so relatively melt poor compared to the Ethiopian Plateau, when they're both underlain by a mantle plume? And the Turkana Depression has even experienced a phase of rifting before the mantle plume arrived that would have thinned it and perhaps enhanced the magmatism there. But that's not the picture we see. And we think this could be because of one of two reasons, perhaps. Firstly, the African plate has not been stable. It's been drifting steadily northwards through time. So perhaps the timing of plume-lithosphere interactions between the depression and further north matter. Or perhaps this previous failed rift that we call the Anza rift through the depression may have somehow suppressed its potential to modify further. So firstly, by using plate reconstructions, so reconstructing where the African plate was 30 million years ago when the main flood basaltic province developed, we find that the initial phase of the plume magmatism likely developed below the plateau, not below the Turkana Depression. So looking at the plot on the left, what you can see is mantle transition zone thickness, and that's broadly analogous to the temperature of the mantle. So wherever you see a thin mantle transition zone, you typically have higher, hotter mantle. So on the plot on the right, it explains this. So at low temperatures, the phase composition or transitions happen at different depths compared to when you have hotter mantle, where 660 will be depressed and the 410 would be elevated deeper. So you get a thinner mantle transition zone. So although that's located below the Turkana Depression today, that's not where it was when 30 million years ago, when the mantle plume first made contact with the plates. It was actually the Ethiopian Plateau and flood basaltic province that was sat right on top of this region. The Turkana Depression, on the other hand, was located a lot further south in mantle that appears to be relatively normal today. And at the time, when the mantle made first contact with the plates, was also a time when a lot of the petrological estimates suggest that the mantle was slightly hotter. So perhaps it's this initial plume impact that governs plate modification. But the Turkana Depression had already experienced a phase of rifting, like we said before, that would have thinned it, and perhaps a thinner lithosphere could have enhanced the melting. But instead, here it seems to have suppressed the depression's potential for further modification. So when Anza rifting happened, that failed rift, it would have dehydrated the lithosphere and rendered it more dry and refractory, and therefore less prone to further melting, because it would have already depleted it in all of its volatiles. So perhaps this lithosphere is stronger and is affecting how further modification happens. So even though there was a gap in time of about 40 million years between when this phase of rifting developed and the plume arrived, so there would have been some thermal re-equilibration, it probably would have kept the lithosphere dry, because there's no, say, subduction zones nearby, which would have added volatiles and rehydrated the lithosphere. So through time, we would have expected this lithosphere to remain dry and dehydrated, and therefore more resistant, perhaps, to further melting. And that's what we see in our wave speeds. We see wave speeds that are persistently fast below the Anza rift. So as well as resisting further thermal and magmatic modification, the failed rift system actually looks to have avoided any subsequent rifting that developed in the Cenozoic. So, for example, all of the rifting below the lake is focused to the west and below the lake in the Turkana Depression. So we can see that in our tomographic models. So all of the slow wave speeds are located right below the lake and to the west of it. However, below Anza, further east, we have faster wave speed mantle. So it doesn't look to have been modified. So to answer the question of why hasn't rifting just developed straight through the Turkana Depression, instead, we know from seismicity work done by Martin Musila in the Trails group, the rifting actually circumnavigates this failed rift system, and it has done so throughout the Cenozoic. And that could be, like we said before, that it's the lithosphere below Anza, so this failed rift system, is relatively stronger because it's been dehydrated during that older rifting episode. But another interesting observation to come out of these results is southern Ethiopia. So a little bit to the north of that, where all of the seismicity suddenly becomes very distributed. What we can see there is that we also have some quite fast wave speed mantle, so just to the north in southern Ethiopia. And we can see it in the body waves as well as the surface waves. There's this really prominent fast wave speed anomaly going to about 200 kilometers depth. So that's suggesting that there may be some rheologically different lithosphere here. So perhaps, again, something refractory, perhaps Proterozoic in age, that may have influenced how both present-day rifting has developed and becomes a lot more distributed, but also how that old Mesozoic phase of rifting developed, because it seems to mark the northernmost edge of it. So that's an interesting observation as well. So to summarize, I guess the main takeaway from this talk is that pretty much the whole of East Africa is underlain by a mantle plume, the depression included. But despite this, the Turkana Depression doesn't look to have been as magmatically and thermally modified as the Ethiopian Plateau to the north, despite having this thinned lithosphere as well. And we think that's either because the Ethiopian Plateau was lying right on top of the initial plume impact 30 million years ago, when the plume was slightly hotter, and therefore perhaps experienced most of the plate modification. So the Turkana Depression at the time was located over cooler mantle. Or perhaps these failed rift systems have rendered the lithosphere a bit more dry and refractory by depleting it of all of its volatiles in the past, therefore suppressing its potential for further modification and rifting. So it's made it stronger, making rifting want to avoid it. So I thought I'd summarize with a schematic that it's both rifting history and initial plume impact that govern plate modification in response to the arrival of a mantle plume. So we can see that the Ethiopian Plateau, very heavily modified, very gradational moho, and an LAB that's really not very clear because of lithosphere now looks seismically similar to what is a stenosphere. Whereas the Turkana Depression generally has a sharp moho and a clear lithosphere-stenosphere boundary, except for where rifting has developed in most recent times, so below the lake and to the west of it. But it's probably because of this older phase of rifting that's made it more resistant to any subsequent modification. Right, and just for anyone interested, this work, like I said, it relates to the Trails project, which is a big multi-institutional, multidisciplinary project. And we've all approached understanding the Turkana Depression in very different ways. So we've each used different seismological techniques to study the structure in this region. And I've listed here some studies that have come out of this. So if anyone's interested, yeah, please look into this. And thank you. I'm happy to take any questions.
Thank you so much, Rita. It was a lovely presentation. Just a reminder that the Q&A is still open. So if you have questions that are coming to mind now, like keep popping them in, and we have a little bit of time where we can go through these. Rita, I don't know if you can see the Q&A, but for the purposes of all the attendees who can't see the unanswered questions, I'll read them out and relay them to you, if that's all right.
Sure. Yeah.
So the first question I have here from a couple of questions from the same person. So this is from Bruno.
Yeah.
This first question is, looking at the East Africa rift system, is there any recorded impact from the ocean loading effects generated from the Indian Ocean?
Good question. So I'd say that's not something I've looked into. So I wouldn't know the answer to that. But I know that pretty much all of this, so this failed rift system in Anza, extends pretty much all the way to the Indian Ocean. So we think that all of this region may have been significantly stretched, perhaps to greater amounts than the Turkana Depression that we've been looking at, where we have sort of seismograph stations. But yeah, I don't know about ocean loading. Yeah, happy to chat about this.
No, that's that's more than so there is a second question,
Yeah.
which is, how can the authors relate their work to data in the Moho determination over Ethiopia? And there's a reference to Anden et al. 2019. Is that something you can answer?
So can you repeat the question, please? How do we relate the work to the Moho determination in the Ethiopian Plateau?
From satellite data.
From satellite data. So satellite data, so there is satellite, so gravity data below the Turkana Depression as well, as to the north. But it broadly is consistent, I guess, with what we determine seismically. But I know gravity is a little bit more non-unique compared to our seismological analysis, which is a very tight constraint on where we would put the MOHO. But broadly speaking, our results are pretty consistent. And I know that in the gravity work that's been done by the Eagle project further north, so I've just shown here the seismic results that show this thick low crustal intrusion layer. It's required in the gravity analysis as well, further north, but I don't show that here. But yeah, it's a good question.
Thank you. So there's another question that's come through from James Ponder that says, great talk. The current rift skirting Anza is effectively moving through an Anza step over. Could it be that this is extra weak, brackets, and nicely oriented, rather than the rift being stronger?
Possible. So I know that, yeah, there has been work. There has been work looking into can you reactivate faults at this angle if you're going to develop the rifting through here, and it could be a possible scenario. It probably makes it less favorable, but I guess it depends on whether you think the crust lies in the strength of the lithosphere lies in the crust or mantle lithosphere. So an idea we've developed in the group is that it's probably related to the crust-mantle ratio below the Turkana Depression. So the mantle lithosphere is generally considered stronger than the crust. So we think that because Anza was pre-rifted, at that time, the crust would have been thinner, the mantle would have then re-equilibrated, and then you would have ended up with a thicker or a higher mantle to crust ratio than you would have had to the west of it, which didn't experience that initial Mesozoic phase of rifting. So over there, the crust would have still have been thicker relative to the mantle lithosphere. So that's the idea, I guess, we've developed in the group. But yeah, we can't preclude the fact that reactivating at an awkward angle might also have an impact, I guess.
No, that makes sense. I guess that leads nicely into the question that I was going to ask, which was, you very nicely presented two different hypotheses. That's the relative moving position of the plume versus the predisposed weakening of the lithosphere from the failed rift. Were there any other sort of hypotheses or from any other analogues that you kind of binned off immediately and didn't consider, or perhaps any other hypotheses you might think to investigate in future?
Yeah, so I think those are the two main ones. So we think the state of the lithosphere at the time of plume impingement matters. So whether it's been pre-thinned, pre-rifted, longevity above a plume as opposed to initial impact might also matter. But that's quite hard to test, I guess, given our seismic results. I think someone who's can model this might be something to look into. But yeah, I think those are the two main ideas, I suppose, that we have.
Okay, no, that makes sense. I did just have someone with their hand up. With a webinar on Zoom, I don't have the permission, I don't think, to unmute someone to speak. So if you do have a question, please keep typing in the Q&A. If you can't access the Q&A for whatever reason, please do also use the chat. Okay, I've had another question come through. This is from Adina Pusok, that again says, great talk. From your results on the LAB depths, the lithosphere in Turkana still seems to be thinner compared to the lithosphere beneath the Ethiopian Plateau. Even if the Turkana lithosphere is dry and depleted due to previous rifting, why would melt be focused beneath Ethiopia and not Turkana?
Yeah, so yeah, the LAB is thinner, or similar broadly to the Ethiopian Plateau. That's not to say there's not any partial melt in the asthenosphere. And we're not trying to say that there hasn't been any magmatism. I suppose below the depression there definitely has been some, but definitely not to the same degree as further north. We think it's likely that any sort of low volume magmatism that would have occurred, or low degree magmatism that would have occurred during Anza rifting, would have depleted it from its volatiles and therefore made it less likely to be able to melt. But perhaps that leads on to perhaps initial plume impact plays a bigger role than the rifting, than the previous rifting phases. Yeah, it's something we're still looking into, I guess, trying to piece the story together. Yeah, because there definitely is melt, just not to the same degree. Perhaps initial plume impact matters a lot. Yeah, so looking into that.
That makes sense. We do have one more anonymous question. I appreciate you've answered quite a few questions, so I won't just barrage you for the next 20 minutes,
Okay.
but they're still coming through. So this one moves away a little bit from East Africa, but I think trying to refer to an analogous system. So forgive me for the pronunciation of this, the Kutch region in Gujarat, India, is a failed rift system and also had reunion plume impact, which led to the Deccan traps. So if we find some anomaly in the 410 and the 660 discontinuity in present day, is it because of the reunion impact, or do you think the anomaly could possibly be a new thermal anomaly?
Yeah, so I mean that's quite a long time ago, I think, from the reunion anomaly, whereas this might be a lot more recent. So we're making an assumption here, essentially, that where the thinnest mantle transition zone is today, and where the plume likely is today, is probably where it was 30 million years ago, when the flood-basaltic province first developed. So it's possible there's been some change in the mantle lithosphere, well, in the mantle and the plume location, but I think that's generally less likely to be the case. But yeah, definitely something to look into, I think. Yeah, I don't know much about the reunion and that older phase of rifting near the Deccan traps, but yeah, might be something good to chat about.
No, that sounds good. So we just have one more question that's here. I'd say we maybe this and then one more, and then I think you're good. You're off the hook. So this question says, thank you for your presentation. Looking at slide 18, is there a correlation between surface heat flow and the temperature derived when wave speeds were converted?
We haven't looked at that direct comparison. There is heat flow estimates throughout the depression, and they are generally high, and they do generally agree with these elevated mantle potential temperatures in the asthenosphere. And they all pretty much agree that there must be a relatively thin mantle lithosphere below the region. But it's not something I've looked into, so I don't know much about heat flow data, whether it's or related to crustal effects or something deeper. But yeah, definitely a good idea to look into that.
Cool. Okay, well, it sounds like you've got lots of
Yeah,
lots
lots
of
to
potential
think about.
avenues, lots of really good suggestions.
Yeah,
No more questions that have come through, so I think given it's nearly 1:45, we can kind of draw a close there. Just to say thank you again to our speaker, Rita. It was really great to have you along.
no problem. Thanks for having
This
me.
was our last this was our last COMET webinar for the year, and we're in the process of confirming our talks for the start of 2025. So please keep an eye on your inboxes, and details for our talks from January and February will be with you very soon. Otherwise, thanks very much and see you next time.